Hello there, and welcome to the Sleepy Science Channel. Tonight, we're going to drift into the unknown, into the questions that science has not yet solved. For all the discoveries we've made, the universe is still filled with puzzles, paradoxes, and quiet mysteries that no one can fully explain. Some are cosmic, stretching across galaxies and black holes. Others live here on Earth, in the oceans, the atmosphere, and even in our own bodies. These unanswered questions remind us that science is not a book of final truths, but an endless story still being written. Each mystery holds a doorway to wonder, a reminder that we are explorers in a universe far bigger than we can yet comprehend. If you enjoy drifting off to scientific wonders, feel free to like and subscribe. Or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let these questions carry you. And if you're ready, let's begin. We still don't know why the universe exists at all. It seems like the most basic question imaginable. Why is there something instead of nothing? And yet science has no answer. Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the Big Bang. But why there is a universe at all, why there are laws that allow it to exist, remains unsolved. Quantum physics suggests that what we call nothing is not truly empty. Even the vacuum of space teems with activity, fleeting particles that flicker into being before vanishing again. Some physicists suggest that the universe itself may have arisen in the same way, that absolute nothingness is unstable, and something must always emerge. Others argue that perhaps our universe is only one of countless universes in a vast multiverse, each popping into being with its own laws. But if that's true, we are only pushed back to a deeper question. Why should the multiverse itself exist? Philosophers sometimes propose that existence is simply the natural state, that non-existence is impossible. Perhaps reality in some form must always be. But these are ideas we cannot test. No telescope, no particle collider can measure why there is being instead of nothing. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature, all exist on a foundation we cannot explain. The fact that reality is here at all remains the deepest mystery we face. The spark that set the cosmos in motion remains a mystery. We can trace the universe's story back nearly 14 billion years, to an age when it was a hot, dense fireball. We call this beginning the Big Bang. But what actually caused it? That remains unknown. Cosmologists have pieced together a detailed history from the moment the universe was only fractions of a second old. In that first instant, rapid expansion, called inflation, may have blown space itself wide open. But what triggered inflation? Why did it start? And why did it end? These questions remain unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others suggest that the Big Bang was not the first event, but only one moment in a cycle of births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the new James Webb, give us snapshots of the infant universe. But none can peer into the first instant itself. We know the universe began. We can measure its age, chart its growth, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, is a mystery, still hidden in the dark. Time always flows forward, but no one can explain why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat moves from hot coffee into the air, but never the reverse. Time, in our experience, only flows one way. This is called the arrow of time. What makes it strange is that the fundamental laws of physics don't require this. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations are symmetrical. Nothing in them demands that time should only advance. And yet, our entire world depends on this one-way street. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an exceptionally ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such a low entropy condition that time could even have a direction? Some physicists think the arrow of time might emerge from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time's direction is something we live inside of, every second of our lives. And yet, why it flows forward, and only forward, remains one of the most haunting mysteries of science. Most of the universe is made of something we cannot see. When astronomers measure the way galaxies spin, they find something strange. Stars near the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is inescapable. Most of the mass in the universe is not visible to us. We call it dark matter. Dark matter neither glows nor absorbs light. Telescopes cannot see it directly, yet we know it must be there because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves faint ripples in the pattern of the cosmic web. So what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMP, or weakly interacting massive particles. Others suggest actions, ghostly particles that barely interact with ordinary matter. There are even theories that dark matter could be black holes formed in the earliest moments after the Big Bang. Despite enormous effort, we still don't know. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, remains one of the universe's greatest unsolved mysteries. An invisible force is stretching space apart faster and faster. In the 1990s, astronomers studying distant supernova expected to see the universe's expansion slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not just expanding, it is accelerating. This means some unknown energy is embedded in space itself, pushing galaxies away from each other at ever-increasing speeds. We call it dark energy, though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos, yet we don't know what it is. One idea is that it is a property of the vacuum, a kind of constant energy present in empty space. Another possibility is that it points to new physics, perhaps a dynamic field that changes over time. Some theories even suggest it could be a sign that our understanding of gravity itself is incomplete. What makes the mystery even more unsettling is its consequence. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift farther apart until only empty space is left. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand shaping the ultimate future of the universe. The laws of physics seem tuned for life in ways we don't understand. The universe appears balanced on a knife's edge. If gravity was slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different by a fraction, atoms would not bind together. Even the tiniest changes in the constants of physics could erase the possibility of life altogether. This puzzle is known as the finituning problem. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or nuclear forces to take the strengths they have. And yet, if they were different by even a little, our universe would be lifeless. Some argue this is coincidence. Others suggest that countless universes exist, each with different laws, and we simply live in the rare one where life is possible, a cosmic lottery win. Another idea is that there may be a deeper principle, still undiscovered, that forces the laws to take these exact values. For now, we cannot say. But when we look around at stars, planets, and the fact that we can even ask this question, we're reminded that the universe feels improbably, uncannily suited for life. And why that is so remains one of science's greatest mysteries. No one knows if the universe goes on forever or ends somewhere. The observable universe is vast, about 90 billion light-years across, but we cannot see beyond it. Light has only had so much time to travel since the Big Bang, and so there is a horizon we cannot look past. But what lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions, with no boundary at all. If so, then space may contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. Scientists search for answers in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. So far, the evidence suggests that the universe is very nearly flat, but this does not settle the question of whether it is infinite. For now, we don't know if the cosmos stretches without end or if it loops back on itself. The true size and shape of the universe remain hidden, just beyond our reach. Beyond the horizon of what we can see, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years. But beyond that lies a region forever hidden, the unobservable universe. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues, but we can never know exactly what is there. Perhaps it is much the same. Galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is radically different, with regions governed by different conditions, or even different physical laws. Some theories of inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our observable patch is just one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest of the universe is out there, silent and unreachable, a permanent unknown. Some scientists believe there are other universes, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. It suggests that our universe may not be unique, but one of countless others. Each universe could have different laws of physics, different histories, even different numbers of dimensions. The concept arises naturally in some theories. Inflation may create bubble universes, each budding off with its own conditions. String theory predicts a vast landscape of possible realities. In such scenarios, our universe is simply one outcome among many. This could even explain fine-tuning. We live in a universe suited for life because only in such universes can observers exist. But there is a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross the boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science, because an idea we cannot test may never be more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. Space and time may be woven from deeper rules we haven't discovered. Einstein's general relativity shows us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But what, at the deepest level, is this fabric made of? At the smallest scales, relativity and quantum mechanics clash. Space and time seem smooth in relativity, but quantum theory suggests that everything should be grainy, fluctuating, and uncertain. Reconciling these two views is one of the greatest challenges in science. Some ideas suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps a network of quantum information or entanglement patterns that give rise to geometry. In this picture, what we call space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Others wonder if time itself is even real, or if it is an illusion created by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds. Yet the stage itself may not be what it seems. What they truly are remains one of the most profound unanswered questions in science. A single particle can be in two places at once, and we don't know how. Quantum mechanics tells us that particles don't have definite positions until we measure them. Instead, they exist in a superposition, a kind of probability cloud, where many outcomes are possible at once. An electron can be here and there, passing through both slits of an experiment simultaneously, interfering with itself like a wave. Only when we look does the particle choose a place. This is not just theory. Experiments have shown superposition at work, not only with electrons, but with molecules thousands of times larger. Physicists can even create delicate states where objects exist in overlapping possibilities. And yet, no one truly understands what it means. Does the particle physically exist in two places? Or is superposition just a reflection of our incomplete knowledge? Some interpretations suggest multiple realities split, one where the particle lands here, another where it lands there. Others suggest reality itself is fuzzy until it is measured. Whatever the case, the ability of a single particle to seemingly be in two places at once remains one of the strangest, most unsettling mysteries of modern science. Entangled particles echo each other across light years, defying explanation. When two particles become entangled, their properties link in a way that defies distance. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, because it seemed to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments confirm entanglement is real. Photons, electrons, even small groups of atoms have been entangled and separated by kilometers. No signal appears to pass between them, but the correlations remain perfect. It is as though nature itself keeps a hidden ledger, ensuring that the outcomes stay in sync. What does this mean? Some physicists suggest reality is non-local, that the universe is woven together more deeply than space and time allow us to imagine. Others think entanglement may point to hidden variables we haven't yet discovered. Still others propose that information itself may be the foundation of reality. We use entanglement in quantum computing and secure communication, yet we cannot say why it works. The universe whispers across distance, and we still don't know how. No one knows why observing something seems to change what it is. One of the strangest discoveries in physics is that the act of measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when no one is looking, creating interference patterns on the screen. But if we measure which slit a particle goes through, the wave-like behavior vanishes. The outcome changes simply because we observed it. Why should this be? One explanation is that the wave function, the mathematical description of all possible states, collapses into a definite outcome when observed. But what counts as an observer? Is it a measuring device? A human consciousness? Or is collapse just an illusion, hiding deeper laws we don't yet see? Some interpretations say every possibility happens, branching into multiple universes. Others suggest that particles only appear definite when information about them becomes irreversible. None of these ideas have been proven. What we do know is that the line between observer and observed is not as simple as we once believed. The universe seems to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we don't know why. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, and governs the motion of stars. And yet, compared to the other forces of nature, it is unbelievably weak. A small magnet on your refrigerator can easily overcome the pull of the entire Earth. Why is this? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate on tiny scales with enormous power. Gravity, by comparison, is feeble. Physicists have tried to explain this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that the true scale of gravity is strong, but it is masked by unknown physics at small distances. Despite centuries of study, we still don't understand why gravity is so much weaker than the other forces. This imbalance is not just a curiosity, it is fundamental to the structure of the universe. Without it, stars and galaxies could not exist. The weakness of gravity is the quiet mystery that makes the cosmos possible. Einstein's universe and the quantum world both work, yet they refuse to fit together. General relativity describes the large-scale universe with unmatched precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Each theory has been tested to extremes, and both pass every experiment we can throw at them. But they do not agree with each other. When we try to describe situations where both matter and gravity are quantum, like inside black holes, or in the first moments of the universe, the equations break down. Infinity piles upon infinity. The two frameworks are mathematically incompatible. Physicists have searched for decades for a theory of everything that unites them. Candidates like string theory and loop quantum gravity offer tantalizing possibilities, but no experiment has confirmed them. Without a unifying theory, we cannot truly understand the birth of the cosmos or the nature of space-time at the smallest scales. The fact that our two most successful theories describe different realities is one of the greatest paradoxes in science. Both work perfectly, and yet, together, they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity is so strong that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density, a singularity. But infinity is usually a sign that our math has failed. What truly lies at the heart of a black hole? Some think the singularity is real, a place where the known laws of physics break down. Others believe a deeper theory, perhaps quantum gravity, will replace the singularity with something else. A loop of space-time, a finite core, or an entirely new kind of object. We cannot see inside. The event horizon hides the interior completely from view. For now, the heart of a black hole is sealed away, beyond observation and beyond certainty. It remains one of the most inaccessible mysteries in all of science. We still don't understand what singularities really are. A singularity is a place where our equations predict infinities, density without limit, curvature without bound, time and space collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one. But what are they, really? Are singularities actual features of nature, or are they signs that our theories are incomplete? Many physicists believe they point to the limits of Einstein's relativity. Somewhere beyond, a new theory, one that merges relativity with quantum mechanics, must take over. In that theory, the infinities might dissolve into something finite and describable. Until then, singularities remain puzzles at the edge of physics. They are places where our understanding stops and our models break. What lies beyond them is hidden, waiting for a deeper theory of reality. Whether information vanishes inside a black hole is an open question. When matter falls into a black hole, it seems to disappear forever. But in physics, information, the details about the state of a system, is supposed to be preserved. So what happens to the information locked inside a black hole? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, the laws of quantum mechanics would be violated. If it escapes, then somehow the information must leak out through the Hawking radiation, a process no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think the information is stored on the event horizon itself. Others argue that black holes might connect to other regions of space-time, allowing the information to escape. Still others think our very understanding of quantum mechanics may need revision. The fate of information in a black hole is one of the most important open questions in physics. It touches not only on black holes, but on the deepest foundations of reality. Hawking radiation is predicted, but no one has ever seen it. In the 1970s, Stephen Hawking made a stunning prediction. Black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales. Eventually, they could evaporate entirely. This radiation, now called Hawking radiation, is one of the most famous predictions in modern physics. Yet we have never observed it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle of radiation. Detecting it directly may be impossible with current technology. Still, the idea has huge consequences. It ties together quantum theory, relativity, and thermodynamics. It suggests that black holes have a temperature, and that space-time itself is more dynamic than we realized. Laboratory experiments have tried to create analogues of Hawking radiation using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will reshape our understanding of black holes. If it does not, something even stranger must be happening at the edge of space-time. Black holes may even be doorways to other worlds. We don't yet know. Black holes push physics to its limits. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest that black holes could connect to other regions of space-time, tunnels known as wormholes. In theory, entering a black hole might lead elsewhere, but this remains speculation. Wormholes, if they exist, may be unstable. The intense gravity of a black hole might destroy anything that tries to pass through. And yet, the mathematics leaves the possibility open. Some physicists suggest that the singularity at a black hole's center could mark a bridge to a new universe, with its own space and time. Others think black holes might recycle information, seeding the birth of new cosmic regions. For now, we cannot test these ideas. No signal can escape a black hole's interior, and so its secrets remain hidden. Still, the idea that black holes may be more than cosmic graves, that they could be gateways to something beyond, is one of the most tantalizing mysteries of all. We still can't explain how the very first stars were born. When the universe was new, it was a dark, simple place. There were no galaxies, no planets, no metals or complex chemistry. Only clouds of hydrogen and helium drifted in the expanding cosmos. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages and lighting the universe for the first time. But exactly how this happened remains a mystery. These first stars, called population the third stars, would have been enormous, hundreds of times the mass of our sun, burning hot and bright, but living only for a few million years before exploding as powerful supernovae. They seeded the cosmos with the first heavier elements, paving the way for later generations of stars and eventually for life. The problem is, we have never seen one. No population the third star has been observed. They lived and died so quickly, so long ago, that direct evidence is missing. Astronomers look for indirect clues in the chemical fingerprints of ancient stars, hoping to find hints of their violent births. The James Webb Space Telescope may finally glimpse their light, but for now, the exact process that sparked the first stars remains one of the great open questions in astronomy. Some galaxies formed supermassive black holes far too quickly. At the heart of nearly every galaxy lies a supermassive black hole, millions or billions of times more massive than our sun. We know how black holes can grow, by swallowing gas, stars, and even other black holes. But in the early universe, we see black holes that grew far too large, far too fast. Some of these giants already existed less than 1 billion years after the Big Bang. According to our models, there simply wasn't enough time for them to grow so big through ordinary processes. This leaves us with a puzzle. Did they form from the collapse of enormous primordial clouds, skipping the small steps entirely? Did they grow from the deaths of massive first-generation stars that collapsed into black holes much larger than we expect? Or is there a mechanism we hadn't discovered yet, allowing them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. For now, they remain cosmic enigmas, giants that should not exist so soon after the universe began. No one knows why so many galaxies take on spiral shapes. When we imagine galaxies, we often picture elegant spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one of them. But why should galaxies form such intricate spiral patterns? The answer is not clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up as they pass, creating the illusion of permanent arms. Another theory suggests that spirals may be shaped by interactions, galaxies tugging on each other with gravity, stirring stars into curving arms. Simulations can recreate spiral structures, but not with perfect consistency. Spirals are not rare. In fact, they are common. And yet their exact origin and stability remain unsettled. Why some galaxies form beautiful spirals while others become elliptical blobs is still an open question in astrophysics. When we look at the night sky and see the Milky Way stretched across it, we are looking from inside one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts flash across the cosmos, and their cause remains a mystery. In 2007, astronomers detected a powerful radio signal lasting only a few milliseconds. Since then, hundreds more have been found, scattered across the sky. These signals are called fast radio bursts, or FRB. Each one releases as much energy as the sun does in a year, but in the blink of an eye. What causes them? Some FRBs repeat, suggesting they come from ongoing processes like magnetars, highly magnetic neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events such as the collapse of a star or the merger of compact objects. But no explanation fits them all. FRBs travel across billions of light years, distorted and stretched by the matter between galaxies. They may even help us map the distribution of matter across the universe. But until we know their source, they remain cosmic puzzles. Every so often, the universe sends us a brief, powerful shout across the void. We can hear it. We can measure it. But we still don't know who or what is speaking. Pulsars shine with perfect regularity, but their precision still puzzles us. Pulsars are the collapsed remnants of massive stars, neutron stars that spin rapidly, sweeping beams of radiation across space like cosmic lighthouses. Discovered in 1967, they were so regular at first, but scientists wondered if they might be signals from intelligent life. Today we know they are natural, but their precision remains astonishing. Some pulsars keep time better than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star crushed into the size of a city, maintain such stability? The answer lies in their incredible density and strong magnetic fields, but the details are not fully understood. Pulsars can also glitch, suddenly changing their rotation speed in ways we cannot yet predict. These glitches may come from interactions deep within their superfluid cores, where physics is unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still keep secrets. Their rhythms remain some of the most mysterious and precise signals in the universe. Magnetars erupt with strange bursts of energy we don't fully understand. A magnetar is a kind of neutron star, with a magnetic field 1,000 times stronger than a normal neutron star and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden, violent bursts of radiation. Magnetars can unleash more energy in a single second than the sun produces in 100,000 years. We detect them as intense X-ray and gamma-ray flares. But what exactly triggers these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the crust of the neutron star under magnetic stress? Or are they caused by sudden reconfigurations of the magnetic field itself, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have even been linked to magnetars, suggesting they might explain at least some of those mysterious signals. But the full picture is still missing. Magnetars are rare, with only a few dozen known, but their power is staggering. They are reminders that the universe contains engines of energy we still struggle to comprehend. Cosmic rays strike Earth with incredible power, and we don't know where they come from. Every second, high-energy particles called cosmic rays rain down on Earth from space. Most are protons, traveling near the speed of light. Many come from the sun or from supernova. But some are so energetic, so powerful, that we have no idea where they originate. The most extreme cosmic rays carry the energy of a fast-pitched baseball packed into a single particle. No known process should be able to accelerate them to such speeds. They may come from supermassive black holes, from active galaxies, or from exotic processes we don't yet understand. These particles crash into Earth's atmosphere, creating showers of secondary particles that we can detect on the ground. Observatories like the Pierre Auger Observatory in Argentina track them, trying to trace their paths back to their origins. But magnetic fields in space bend their trajectories, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. They remind us that somewhere in the universe, nature runs particle accelerators far beyond anything humans can build. Vast cosmic voids stretch across space, and their origins remain unclear. The universe is not evenly filled with matter. Instead, galaxies form a vast cosmic web, clusters and filaments separated by enormous voids. Some of these voids span hundreds of millions of light years, nearly empty of galaxies. Why are they there? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty spaces behind. But the largest voids are bigger than expected, raising questions about how they formed. Do they hint at new physics, perhaps in the way dark energy shapes structure? Or are they just statistical extremes, rare but possible? Voids affect how light travels across the universe. They may even offer clues about the nature of dark energy itself. But for now, their true origins remain uncertain. Looking into a cosmic void is like staring into nothingness on the largest possible scale. They are among the loneliest regions in existence, vast expanses with no clear explanation. How the universe will end is still an unanswered question. The universe had a beginning, but will it also have an end? Scientists consider several possibilities, each dependent on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, cooling until stars burn out and galaxies fade, leaving only cold darkness. This is the heat death. In another, the expansion may eventually reverse, pulling everything back together in a big crunch. A third possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms. Which will it be? We don't yet know. Observations suggest expansion will continue, but the details of dark energy remain too uncertain to decide. The universe may last for trillions of years, or it may meet a more dramatic fate. For now, the ultimate future of everything, of stars, galaxies, and life itself, remains one of the greatest unanswered questions of science. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than the speed of light, in a process called inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations seeded the galaxies we see today. But what caused inflation? That remains a mystery. Some theories propose a field of energy, the inflatum, that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of space-time itself. We see its fingerprints in the cosmic microwave background, where patterns match what inflation predicts. But the true cause, and whether inflation really happened as described, is still debated. Something made the universe grow unimaginably fast, creating the stage for everything that followed. But the spark that drove this inflation is still unknown, a hidden chapter in the story of creation. The origin of life on Earth is still unknown. Life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows that microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea is that life began with simple molecules self-organizing into chains capable of storing information, perhaps RNA before DNA. Another is that life emerged from the energy-rich environment of hydrothermal vents on the ocean floor, where hot water, minerals, and chemistry combined. Still others propose that life's building blocks may have arrived from space, carried on comets or meteorites that bombarded the young Earth. Each idea has support, but none are proven. Scientists have managed to create amino acids and other basic molecules in laboratory conditions thought to mimic the early Earth. But producing a fully living system remains beyond reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we uncover clearer evidence, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. We don't know if life began in the ocean or on land. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems like the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide rich chemistry and constant energy. Many scientists believe life may have begun there, with molecules assembling inside natural mineral compartments. But there is another possibility. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the reactions needed to form life's building blocks. Ultraviolet light from the sun, often destructive, could also have powered key steps in these reactions. Both environments seem plausible. Each offers strengths, and each faces challenges. The ocean dilutes molecules, making it harder for them to interact, while land-based pools may have been too unstable. Until stronger evidence emerges, we don't know whether life first stirred in the deep oceans or in the shallow waters of land. The answer remains hidden in the deep past, in rocks and fossils that have long since transformed. No one knows how the first living cells were formed. Life is defined not just by chemistry, but by organization. Modern cells are intricate structures, with membranes that separate them from the outside world, and with molecular machines carrying out countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules, naturally present on the early Earth, formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed energy and molecules to flow while protecting fragile chains of RNA or proteins. Over time, the chemistry inside could have become more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously in the right conditions. But how the leap from these primitive compartments to the complexity of a living cell occurred is still unknown. This transition from disorderly chemistry to the first organized cell remains one of the great mysteries of biology. Until we understand it, we cannot say how life truly began. DNA chose a very specific shape, But why it did remains a mystery. All life on Earth uses the same molecule to store information: DNA. Its double helix is elegant and universal, carrying the instructions for every organism. But why this molecule? And why this shape? Chemistry allows for many possible ways to store information. RNA, for instance, is simpler and may have come first. But somewhere in life's early history, DNA took over as the master code. Its stability, its ability to replicate reliably, and its capacity to carry immense amounts of information made it uniquely suited. Yet we don't know why DNA's specific structure, a double helix with precisely paired bases, became the solution that all life depends on. Was it inevitable, dictated by chemistry? Or was it an accident, a single successful outcome among many failed alternatives? The universality of DNA suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question, hinting at deep mysteries in the chemistry that underpins existence. The origins of viruses are still unclear. Viruses are strange entities. They are not alive in the traditional sense. They cannot reproduce on their own, relying instead on hijacking the machinery of living cells. Yet they are not merely inert molecules. They evolve, adapt, and influence the course of life on Earth. Where did they come from? Some scientists think viruses are relics of the RNA world, survivors from before fully living cells evolved. Others believe they began as pieces of genetic material that escaped from cells and learned to copy themselves. A third possibility is that they were once living organisms that became stripped down to their simplest form. The truth may be that viruses arose in more than one way, their origins as diverse as life itself. What is clear is that they are ancient. They may even have played a crucial role in the evolution of complex life, transferring genes between organisms. Viruses blur the line between life and non-life, and their beginnings remain one of biology's most enduring mysteries. Some molecules became alive, while countless others did not. We don't know why. The early Earth was a chemical playground. Simple molecules formed everywhere, from deep-sea vents to volcanic pools to lightning-struck atmospheres. Among them, some began to link into more complex chains, like amino acids and nucleotides. But only a tiny fraction of this chemistry crossed the line into life. Why those molecules and not others? What special property allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients came together? Or was it a rare accident, dependent on chance events? Experiments suggest many building blocks of life can form under natural conditions. But creating a self-sustaining, evolving system remains elusive. The leap from chemistry to biology is vast, and we don't yet know how it happened. This uncertainty raises profound questions. If life is inevitable, then the universe may be filled with living worlds. If it was a fluke, then we may be utterly alone. The mystery of why some molecules became alive while others remained inert is one of the most important unanswered questions in science. We still don't know if life exists anywhere else in the universe. Earth is the only place we know where life exists. But with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely that we are alone. Still, despite decades of searching, no clear evidence of extraterrestrial life has been found. We have discovered thousands of exoplanets, many in the habitable zone where liquid water could exist. We know that organic molecules are common in space, found on comets, in clouds, and on distant moons. Mars shows signs of a wetter past. Europa and Enceladus hide oceans beneath their icy crusts. Conditions for life seem abundant. And yet, the silence persists. We have not detected signals, nor found microbes on Mars, nor uncovered alien fossils. It is possible life is common, but hard to detect. Or it may be exceedingly rare, requiring conditions we don't yet understand. Until we find even the simplest alien microbe, the question of whether life exists elsewhere remains unanswered. Could life form from a chemistry completely different from ours? We don't know. All life on Earth is built on the same foundation: carbon, water, DNA, and proteins. But must it be so? Could life exist with a different chemistry entirely? Some scientists think silicon, abundant and capable of forming long chains, could serve as the backbone of alien life. Others imagine organisms that use ammonia instead of water, or exotic biochemistries thriving in methane seas, like those on Saturn's moon Titan. Still others wonder if plasma, magnetic fields, or information itself could host something like life. We don't yet know the answer. All of our definitions of life are shaped by a single example: Earth. It may be that carbon and water are the only real solution. Or it may be that the universe holds living systems stranger than we can imagine. If we discover alien life, it may look nothing like us. It could challenge our very definition of what it means to be alive. How common truly habitable worlds are is still uncertain. Astronomers have discovered thousands of planets orbiting other stars. Many are small and rocky, some in the habitable zone where liquid water might exist. But how many are truly habitable? That is still unknown. Habitability depends on more than distance from a star. Planets need the right atmosphere, magnetic protection, and long-term stability. Some may be scorched by radiation, others frozen by lack of heat. Moons may be habitable too, with oceans beneath their icy crusts, but we cannot yet measure them directly. The galaxy may be rich in habitable worlds, or they may be rare jewels. Right now, we cannot say. Each discovery brings us closer, but the true frequency of Earth-like conditions remains one of the great open questions in astronomy. We still can't answer the oldest question of all: are we alone? For as long as humans have looked at the stars, we have wondered whether life exists beyond Earth. Despite the size of the universe, despite the abundance of planets and the chemistry of life scattered across space, we still have no answer. We listen for signals with radio telescopes. We send probes to planets and moons. We analyze the atmospheres of distant worlds for signs of life. But so far, the silence is complete. It may be that life is common, but intelligent civilizations are rare or short-lived. It may be that life is rare at every level, and we are a singular accident. Or it may be that life is everywhere, but hidden from us by distance or difference. The question remains open. Are we a lonely spark in a vast, empty universe? Or one voice in a cosmic chorus we have not yet heard? Until we find evidence, the answer to this oldest of questions remains unknown. Consciousness arises from the brain, but we don't know how. Every thought you have, every memory, every flicker of awareness seems to arise from the brain. Scientists can measure electrical signals moving across neurons, they can switch awareness off with anesthesia, and they can even track the brain's activity when you focus on a picture or a sound. Yet none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you see a sunset, but it doesn't explain why that experience comes with the glow of red and gold inside your mind. It shows circuits for sound, but it doesn't explain why hearing your favorite song feels so moving. Researchers have ideas that consciousness appears when information spreads across the brain or when neurons form certain patterns, or even that awareness is a deeper property of the universe itself. But none of these ideas truly explain the leap from matter to mind. Consciousness is the most ordinary thing. It's what you're experiencing right now. And yet, when we try to explain it, it slips through our fingers. We know it arises from the brain, but the how remains the deepest mystery of all. Dreams fill our nights, but their purpose is still unknown. Every night, as you sleep, your mind conjures worlds. Some are vivid, filled with people and places you know. Others are strange and fragmented, dissolving as soon as you wake. These are dreams, and though we all experience them, no one truly knows why they happen. Some scientists think dreams are the brain's way of practicing. They may replay memories, strengthening useful connections. Others believe dreams help regulate emotion, allowing you to work through fear, sadness, or conflict in a safe, unreal space. Some say they are simply random firings of a sleeping brain, patched together into stories. What makes dreams more puzzling is that they can be so powerful. A nightmare can wake you in terror, even though you are safe in bed. A good dream can leave you smiling all day. Sometimes, dreams even solve problems. Writers, artists, and scientists have all described breakthroughs that came to them in sleep. We know the brain is active while we dream, especially during REM sleep, when the eyes flicker beneath closed lids. But the purpose behind it remains elusive. Dreams are familiar, nighty journeys into strange lands, yet their true meaning is still hidden. Time feels slower or faster depending on us. No one knows why. Think of a moment when time seemed to slow to a crawl, a near accident, a sudden fright, an intense experience. Now, think of the opposite. A holiday that seemed to vanish in an instant, or hours that disappeared when you were fully absorbed in something you loved. Clock time is steady, but our sense of time is anything but. Why? No one knows for sure. Some believe the brain has an internal clock, and that emotions like fear speed it up, while calm states slow it down. Others suggest our brain judges time by the number of events it processes. A moment filled with new details feels longer, a routine one feels shorter. This could explain why childhood summers seemed endless, while adult years slip past more quickly. Novelty stretches our perception, and routine compresses it. But it is only a theory. What we do know is that time in the mind is elastic. It stretches, contracts, and sometimes even seems to stand still. The seconds and minutes are constant, but our experience of them is mysterious, flowing according to rules we don't yet understand. We don't yet understand how memories are stored and recalled. Your entire life, your first day of school, your happiest moments, your deepest regrets, is stored somewhere inside your brain. And yet, how those memories are kept, and how they return when you need them, is still a mystery. Scientists know that memories are not like files in a cabinet. They are patterns of activity across many neurons, spread across different regions. The hippocampus helps weave these patterns, acting as a kind of index. But exactly how the brain encodes a memory and later pulls it back is not fully understood. Sometimes, memories change when we recall them, being reshaped before they are stored again. Sometimes we even create false memories that feel completely real. Why do some memories last a lifetime, while others fade in days? Why does a certain smell suddenly unlock a vivid scene from childhood? Experiments show glimpses, neurons that fire when a specific face is seen, brain activity that mirrors memory recall. But the full picture is missing. Memory is the glue that makes us who we are. And yet the machinery behind it, how moments become part of us, and how they return years later is still unknown. Our emotions run deep, but their origins remain mysterious. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know that emotions involve the body as well as the brain. Your heart races when you're afraid. Your stomach knots when you're anxious. Tears well up when you're sad. But the origins of these feelings are still debated. Are emotions hardwired, ancient survival tools built into our biology? Or are they constructed by the brain, shaped by culture, memory, and interpretation? We know certain brain regions play a role: the amygdala for fear, the insula for disgust, the prefrontal cortex for regulation. But no single emotion center exists. Music can bring goosebumps. Scents can trigger sudden nostalgia. Sometimes, we don't even know why we feel the way we do. Emotions are powerful guides, steering our choices often more than reason does. Yet the way they arise, the way they take hold of the body and the mind, remains one of the most intimate mysteries of being human. Creativity appears in sudden sparks, but we don't know where it comes from. An artist stares at a blank canvas, a writer at an empty page, a scientist at an unsolved problem. Hours may pass with nothing, and then suddenly an idea arrives, clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it is the brain mixing and matching old ideas in new ways. Others think it requires stepping away, letting the subconscious work while the conscious mind rests. Many breakthroughs in history have come not at desks, but in dreams, showers, or quiet walks. Brain scans suggest different networks are involved, some generating ideas, others judging them. But this still doesn't explain the moment of inspiration. Why does the solution arrive suddenly, with such force? Why do some people overflow with creative ideas, while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place where ideas come from, that quiet leap from nothing to something, is a mystery we still cannot explain. Déjà vu makes the present feel repeated, and no one knows why. You step into a room you've never been in before, and suddenly, everything feels strangely familiar. You know what will happen next, though you don't. This is déjà vu, and it remains one of the strangest mysteries of the mind. Scientists suggest it may be a trick of memory. Perhaps the brain misfires, creating a false signal of familiarity without a real memory behind it. Others think it happens when one part of the brain processes an experience slightly before another, making the moment feel like a repeat. Still others suggest it comes from similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu so mysterious is the intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, and that the brain sometimes tricks us in ways we don't yet understand. Placebos can heal, but the power behind them is still a mystery. Imagine taking a pill, being told it will ease your pain, and then actually feeling better, even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even calm symptoms of Parkinson's disease. The effect is thought to come from expectation. The belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers, alter brain chemistry, and affect the immune system. What makes the placebo so strange is that it can work even when people know they're taking one. Somehow, the ritual of treatment, the pill, the doctor, the belief, taps into hidden healing pathways. But why some people respond strongly to placebos and others do not is still unknown. The placebo effect blurs the line between mind and body, showing us that belief itself can sometimes heal in ways we still don't fully understand. We don't even know why we need sleep at all. Every night, we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why do we need it? Sleep is dangerous if you think about it. In the wild, an animal that sleeps is vulnerable. Yet every species does it in some form. That suggests sleep is essential, but essential for what? Some scientists believe sleep helps the brain store memories and learn. Others think it clears away waste, cleaning the brain of harmful buildup. Sleep may restore energy, regulate emotions, and strengthen the immune system. It may even help the brain rewire itself, keeping connections balanced. And yet, no single explanation fits all the evidence. Different animals sleep in very different ways. Dolphins sleep with only half their brain at a time. Some birds sleep while flying. Some creatures need very little sleep at all. What we know for sure is that without sleep, minds and bodies quickly break down. Why we spend a third of our lives doing it remains one of science's great mysteries. We still don't know why aging happens the way it does. Every living being on Earth ages. Skin wrinkles, hair turns grey, muscles weaken, and eventually the body begins to fail. But science cannot fully explain why aging happens, or why it happens in such different ways across species. One explanation points to our DNA. Each time a cell divides, the protective caps at the ends of our chromosomes, called telomeres, grow shorter. Eventually, the cell stops dividing altogether. Another theory blames damage. Oxygen molecules and other byproducts slowly corrode cells over time, leaving scars that accumulate. Others see aging as a side effect of evolution, a trade-off that allows energy to be focused on reproduction in youth, but leaves the body vulnerable afterward. Yet nature presents exceptions. Some turtles and fish show almost no signs of aging. Certain jellyfish appear able to revert to earlier stages of life, sidestepping decline altogether. Naked mole rats live far longer than expected, showing resilience against many diseases of age. Why do some creatures resist aging while humans succumb to it? And why does the process unfold with such predictability in us? The answers remain elusive. Unlocking this mystery could change medicine forever, but for now, aging is a riddle written into our very cells. The limits of human lifespan remain uncertain. The longest confirmed human life ended at 122 years. But was this the upper ceiling of human biology, or just a remarkable outlier? The truth is, no one knows. Some researchers argue that humans have a hard limit. Beyond a certain age, the body cannot repair itself quickly enough to survive. Evidence suggests that survival rates decline sharply after 110, hinting at a biological cap. Others insist there is no strict maximum, only ever-rising odds of frailty, disease, and chance. What's puzzling is that although average life expectancy has climbed dramatically thanks to medicine, hygiene, and nutrition, the maximum lifespan has barely budged. Almost no one lives past 115, no matter where or when. Still, scientists search for ways to extend life further. They study families of superagers who remain healthy into extreme old age. They look for genes that resist disease, and test drugs that slow aging in animals. Could humans someday reach 150 years? Or even 200? The data offers hints, but no certainty. The upper boundary of human life remains hidden, waiting for someone to discover whether it is fixed or can be pushed further. Some animals can regrow entire limbs, and we can't explain how. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it slowly rebuilds it. Even certain worms can regenerate an entire body from a single fragment. In nature, regeneration is surprisingly common, but humans cannot do it, except in the tiniest ways. A fingertip might regrow in a child, but a lost limb never returns. The question is, why them and not us? Scientists studying salamanders find that when they are injured, their cells near the wound seem to reset, rolling back into a flexible state like those of an embryo. From there, the cells grow into muscles, bones, and nerves, perfectly organized. Humans share many of the same genes, yet for reasons we don't understand, our bodies do not use them in the same way. If we could unlock this ability, medicine would be transformed. Damaged hearts could heal themselves. Spinal cords could regrow. Limbs could return. And yet, despite decades of study, the full blueprint of regeneration remains hidden. Why nature allowed some creatures to wield this power while denying it to us is a mystery. For now, regeneration belongs to the salamander, the starfish, and a few others, a miracle we can only watch with awe. Certain creatures live far longer than expected, and we don't know why. Most animals follow a simple pattern. Small bodies live short lives, large ones live longer. Mice live a few years. Elephants live many decades. Humans, with our long lives, are outliers among primates. But scattered across nature are creatures that defy these rules entirely. The Greenland shark glides beneath Arctic ice for centuries, its lifespan stretching more than 400 years. Bowhead whales sing in frozen seas for over 2 centuries. Tiny, naked mole rats live 10 times longer than similar rodents, with remarkable resistance to age-related decline. Some clams have been discovered alive after more than 500 years. Why? Scientists have found clues: unusual proteins that resist damage, DNA repair systems that seem more efficient, metabolisms that move at an incredibly slow pace. But no single answer explains them all. Each species seems to have its own key to longevity, and humans cannot yet copy it. These creatures remind us that aging is not a fixed law of nature, but a puzzle with many solutions. If we could learn their secrets, we might one day unlock new ways to extend our own lives. For now, they remain timeless enigmas of the natural world. Some animals survive being frozen solid, yet their secrets remain hidden. Imagine being frozen into ice, your blood crystallized, your heart silent, your body rigid. For most creatures, this means death, but not for all. The wood frog of North America freezes solid in winter. Its heart stops. Its body stiffens. Yet when spring warmth returns, the frog falls and hops away unharmed. Certain insects and fish can do the same, and tardigrades, tiny water bears, can endure extremes far beyond freezing, surviving in the vacuum of space itself. How do they do it? Some creatures fill their bodies with special antifreeze molecules that prevent ice crystals from shredding their cells. Others use sugars that stabilize tissues during freezing. But the exact details of how their brains, hearts, and other delicate organs survive months without activity remain unclear. If we could master this trick, it might change organ transplants, medicine, even space travel. We could preserve organs for months, maybe place humans into hibernation for long journeys. But for now, the secret belongs only to these hardy survivors, creatures that seem to laugh at the laws of life and death. Whales live for centuries without much cancer, and no one knows how. The bowhead whale can live for more than 200 years, gliding through icy Arctic waters. What makes this astonishing is not just its age, but its health. Despite its massive size, with billions of cells and centuries of time for mutations, cancer is remarkably rare. This is known as Peto's paradox. Larger animals with more cells should, in theory, have higher cancer rates. But whales, elephants, and other giants don't. Somehow, they resist. In elephants, researchers have found extra copies of tumor suppressor genes, like extra layers of defense. In whales, the explanation is murkier. Perhaps their DNA repair systems are unusually strong. Perhaps their metabolism slows damage. Perhaps they have unique biological pathways we haven't discovered yet. If we could unlock this mystery, it might revolutionize cancer treatment for humans. Whales have cracked part of the code of long life without disease. But for now, their secret drifts beneath the waves, unsolved. Birds can sense Earth's magnetic field, but the mechanism is still unclear. Every year, birds migrate across continents. Tiny warblers fly from Europe to Africa. Arctic terns cross oceans, circling the globe. They travel thousands of miles with uncanny accuracy. Part of their secret seems to lie in Earth's magnetic field, but how they sense it remains uncertain. Some evidence points to tiny crystals of magnetite in their bodies, acting as internal compasses. Other research suggests certain proteins in their eyes may let them see magnetic fields as faint patterns of light. But no single theory explains it all. What we do know is that their ability is incredibly precise. Even on cloudy days when the sun and stars are hidden, birds stay on course. Released in unfamiliar lands, they still find their way. It's a sense humans lack, like an invisible layer of reality we cannot perceive. For birds, the world carries directions written into its very fabric, a compass we still don't understand. Monarch butterflies navigate continents with a map we cannot read. Every autumn, fragile monarch butterflies begin an impossible journey. They fly thousands of miles from the northern United States and Canada to a few mountain forests in central Mexico. There, they gather in dense swarms, covering trees in shimmering orange. What makes this migration astounding is that no single butterfly completes the round trip. The ones that return north in spring are several generations removed from those that left in fall. Yet somehow, they arrive at the very same groves year after year. Scientists know monarchs use the sun as a compass, adjusting for the time of day. They may also sense Earth's magnetic field. But how they pass this knowledge between generations, how a butterfly that has never made the journey knows exactly where to go, remains a mystery. It is one of the most breathtaking migrations on Earth, guided by a hidden map no human has ever read. Migrating animals cross thousands of miles, but we don't know how they guide themselves. The natural world is full of great migrations. Salmon hatch in mountain streams, swim to the sea, and years later return to the same stream to spawn. Sea turtles crawl from the ocean onto the very beach where they first hatched. Birds, whales, and insects all travel across the planet with astonishing accuracy. Scientists have discovered clues. Some animals use the stars, the sun, and the tilt of Earth's axis. Some may follow magnetic fields or subtle scents. Yet none of these explanations fully accounts for their precision. How does a bird find the same tree each year? How does a turtle cross an entire ocean to one patch of sand? These journeys remain partly unexplained, guided by senses we do not yet fully understand. Migration is one of life's oldest rhythms, a grand, mysterious dance written into the instincts of animals. Homing pigeons return home from anywhere, and the mystery persists. For centuries, humans have marveled at homing pigeons. Release one hundreds of miles from home, and it will rise into the sky, circle, and then fly straight back to its loft. No map, no guide, just a hidden sense of direction. Researchers have proposed explanations. Some believe pigeons use the sun as a compass, adjusting for time. Others suggest they detect Earth's magnetic field, like a built-in GPS. Still others point to smell, the idea that pigeons build a scent map of their home region and follow it back. But none of these fully explain their uncanny accuracy. Even when released in strange places, under cloudy skies, pigeons still find home. It is a mystery hidden in their biology, a secret compass we have yet to uncover. For pigeons, the world is filled with invisible cues that guide them across the sky. For us, it is still a puzzle unsolved. No one knows exactly how humans first developed language. Language is what makes us human. With it, we share ideas, pass down stories, and build civilizations. But how it began remains one of the greatest mysteries of our past. Our closest relatives, chimpanzees and bonobos, can communicate with gestures and sounds, but none come close to the complexity of human speech. At some point, our ancestors made the leap from simple calls to structured language, complete with grammar, abstraction, and infinite possibilities. But when and how did it happen? Some theories suggest language began as hand signals, with words coming later. Others propose that rhythmic sounds, chants, and songs gradually grew into spoken language. Archaeology shows us carvings and symbolic art, tens of thousands of years old, suggesting the minds that created them were already capable of complex communication. But the sounds themselves left no trace. Language allows us to describe what is not present, to plan, to dream, to imagine. It is both a survival tool and a window into thought. Yet the first spark of language, the moment when humans first spoke, is lost in time. We can only guess at the conversations that began it all. Laughter is universal, but its roots remain a puzzle. Wherever you go in the world, people laugh. The sound crosses cultures, ages, and languages. Babies laugh long before they speak. Groups laugh together, their joy contagious. Yet why we laugh and how it first evolved remains uncertain. Some scientists believe laughter began as a signal of safety. Early humans may have laughed to show others that a threat had passed, turning fear into relief. Others trace it back to primates at play, whose panting sounds during wrestling and chasing resemble laughter's rhythm. But laughter is more than a survival tool. It lowers stress, bonds groups, and releases powerful chemicals that flood the body with calm. Strangely, we laugh not only at jokes, but also at relief, at awkwardness, even at sorrow. Sometimes laughter bursts out when it makes no sense at all. Why should a sound, a breathy burst of air, carry such power? We don't know. What we do know is that laughter is ancient, universal, and mysterious. It is the music of joy, shared across all humanity, its roots still hidden in our past. Music moves us deeply, but science can't explain why. A melody can make us cry. A rhythm can make our hearts race. A song can bind us to memories we thought forgotten. Music has no obvious survival function, yet it shapes human life across every culture. Why? We don't know. Some suggest music evolved as a kind of glue, binding early communities through dance and song. Others think it began as courtship, a way to signal vitality and skill. Still others argue it's a byproduct of language and memory, a beautiful accident of evolution. What makes music even stranger is its power. Stroke patients who struggle to speak can still sing. People with dementia recall lyrics when almost everything else has faded. Music can synchronize heartbeats in groups, can calm newborns, can stir armies to march. Why should organized sound reach so deeply into our minds and bodies? Science has no clear answer. Music remains one of the most universal, mysterious forces in human life, an invisible thread that ties us together. Love is powerful and complex, but its full nature is still unknown. Love shapes human lives more than almost anything else. It binds parents to children, partners to one another, friends across time. It inspires art, sacrifice, and joy. Yet science still cannot fully explain what love is. Biology shows us pieces. Love floods the brain with dopamine and oxytocin, chemicals tied to reward and bonding. Evolutionary theory suggests it developed to keep parents together long enough to raise vulnerable offspring. But these explanations do not capture the full experience. Why does love sometimes arrive suddenly, overwhelming us? Why does it last a lifetime in some cases and fade in others? Why do people risk everything for it, even against reason? Love is not only chemistry or instinct, it is memory, story, imagination, and something more. We can map its effects in the brain, but not its meaning. Love is both universal and unique, an experience shared across humanity, yet different for every person. Its full nature remains one of the most profound mysteries of being alive. Humans cry tears of emotion, and no one knows why. Tears protect our eyes, washing away dust and salt. But only humans shed tears for reasons beyond biology, when we are sad, joyful, frustrated, or even overwhelmed with laughter. Why? One idea is that tears are a social signal, showing vulnerability and drawing empathy. Another suggests they release stress chemicals, though evidence is mixed. Tears may strengthen bonds, making emotions visible to others. What deepens the mystery is that we cry for opposite feelings. Tears come with grief and with joy, with sorrow and with relief. They fall silently in solitude or in the middle of laughter. No single explanation captures all of this. Tears remind us that we are emotional beings, not just logical ones. They make the invisible visible, carrying feelings from inside to the outside world. But the reason humans alone evolved this response remains unsolved, a secret hidden in every tear that falls. Myths appear across cultures in similar forms, for reasons we don't understand. From deserts to islands, mountains to forests, cultures separated by oceans tell stories that echo one another. Myths of great floods, of sky gods, of tricksters, of underworlds, they appear again and again. Why? Some suggest human minds are wired for story, and certain themes arise naturally from shared experience: the fear of death, the hope for renewal, the awe of the sky. Others believe ancient myths spread through migration and trade, leaving echoes in distant lands. Still others wonder if myths are shaped by deeper patterns in the human brain, symbols born from the same inner landscape. Whatever the reason, myths carry truths that cultures find important. They explain the unexplainable, bind communities together, and pass wisdom through generations. But the strange recurrence of similar stories across the globe, appearing where no contact seems possible, remains a mystery. We often cooperate with strangers, and the origins of this instinct are unclear. Humans are unusual among animals. We not only help family and close allies, but also strangers. We donate blood, we build communities, we risk ourselves for people we may never meet. Why? Evolutionary theories suggest cooperation evolved to strengthen groups, giving them an edge over rivals. Others point to reciprocal altruism, the idea that help given will one day be returned. But humans go beyond calculation. We volunteer, we share, we sacrifice, sometimes without any hope of reward. Experiments show even young children choose to help, long before they fully understand rules or society. Something in us seems drawn toward cooperation, but its origins remain unclear. Did it arise from survival needs, or from something deeper, a moral instinct written into our minds? The willingness to help strangers remains one of humanity's most beautiful and most mysterious traits. Civilizations rise and fall, but the deep forces behind them remain debated. Across history, mighty civilizations have grown, flourished, and then collapsed. The Maya, the Indus Valley, Mesopotamia, Rome, all rose to greatness, only to fall. But why civilizations follow this arc remains debated. Some point to climate change, droughts, and disasters. Others to war, corruption, or the exhaustion of resources. Still others believe civilizations carry within them patterns of growth and collapse, cycles that repeat regardless of time and place. The truth may be all of these, or something else entirely. What is striking is how sudden collapse can be. Great cities are abandoned, knowledge is lost, and generations vanish into silence. Civilization itself is fragile, and the forces that make it thrive or fail are not fully understood. We live within a vast and complex society, but history reminds us that nothing lasts forever, and the reasons why remain a mystery. Human curiosity drives us, but its source is still unknown. Why do we wonder? Why do we look up at the stars and ask questions no other creature seems to ask? Curiosity is one of humanity's defining traits, but where it comes from remains unclear. Some say curiosity is an extension of survival, helping us seek food, shelter, and safety. Others believe it grew as an evolutionary advantage, pushing us to explore, to invent, to imagine. But curiosity often goes far beyond survival. It drives us to study galaxies billions of light years away, to decode ancient languages, to ask questions with no practical answer at all. Children show curiosity from the very beginning, reaching for the unknown, asking endless questions. It seems built into us. But why this hunger for knowledge, why this restless drive to understand, is not yet explained. Curiosity pushes us forward, shaping science, art, and exploration. But its source, the spark behind the question why, is still one of life's mysteries. Storytelling is universal, but no one knows why we need it. Every culture tells stories. Around fires, on stages, in books, in films, humans shape words into narratives. Stories carry heroes and villains, struggles and triumphs. They entertain, they teach, they inspire. But why are they universal? Some suggest storytelling is a way to pass on knowledge, wrapping lessons in memory. Others think it binds communities, giving people shared myths and values. Some see it as practice, rehearsing challenges and choices safely in imagination. But stories often go beyond these roles. They create worlds that never existed, fill us with emotions for people who are not real, and linger in our minds for years. No other species does this. Why do humans need stories? Why do we long for them? again and again. We don't know. What we do know is that storytelling is as ancient as language itself, a thread running through every culture, connecting us all. Lightning sometimes forms glowing balls of fire, and we don't know how. Most people know lightning as a flash in the sky, a jagged streak followed by thunder. But there is a far stranger phenomenon that has baffled observers for centuries: all lightning. Instead of a quick bolt, it appears as a glowing sphere of light, floating silently, drifting across fields, or even inside hose. Witnesses describe orbs the size of a grapefruit, glowing orange, white, or blue, sometimes lasting several seconds before vanishing, or exploding with a pop. For centuries, ball lightning was dismissed as myth, a trick of the eyes. But in recent years, credible sightings and even a few scientific recordings suggest it is real. The problem is, no one knows what it is. Some theories describe plasma trapped by electromagnetic fields. Others imagine vaporized silicon glowing after a strike. Some suggest chemical reactions sparked in the air. But no explanation fits every account. The mystery deepens because ball lightning has been seen indoors, even floating through windows without shattering them. It seems to ignore ordinary physics, behaving like both matter and light. Despite thousands of reports, it remains elusive, unpredictable, and unexplained. Ball lightning drifts through history as one of nature's strangest and most beautiful mysteries, a ghostly fire in the sky. Earthquake lights appear in the sky, and no one knows what causes them. During some powerful earthquakes, witnesses report glowing lights in the sky. They take many forms: flickering blue flames along the ground, flashes like lightning above cities, or strange orbs floating over fault lines. These earthquake lights have been described for centuries, but modern cameras have also captured them, confirming they are real. What causes them remains unknown. One theory suggests that stressing rocks during an earthquake releases electrical charges, sparking light in the air. Another idea is that tectonic forces ionize gases near the ground, making them glow. But not every earthquake produces lights, and the appearances vary wildly. In some cases, the lights arrive before the earthquake, leading to speculation that they could act as a warning system. But their rarity and unpredictability make them difficult to study. Earthquake lights are among the most eerie natural mysteries, flashes of otherworldly glow in the midst of chaos, reminders that Earth itself may hold secrets written in fire and stone. Some volcanoes erupt with terrifying force, and the triggers remain mysterious. Volcanoes are among the most destructive forces on Earth. Most eruptions are dramatic but manageable. Lava flows, ash plumes, small explosions. But every so often, a volcano erupts with unimaginable fury, blasting enough material into the sky to alter climate and spread devastation across continents. What makes some eruptions so catastrophic? Scientists know pressure builds as magma rises and gases expand, but the exact tipping point remains uncertain. Some volcanoes sit dormant for centuries, then erupt without warning. Others rumble and smoke for years, but never explode. The mystery lies in what flips the balance from silence to disaster. Events like Krakatoa in 1883, Tambora in 1815, and the eruption of Mount Toba 74,000 years ago unleashed energy on a scale rivaling nuclear weapons. Toba may even have nearly wiped out humanity. Yet modern science still cannot predict which volcanoes will erupt this way, or when. We monitor tremors, measure gases, and scan magma chambers, but the inner mechanics of super-eruptions remain hidden. Volcanoes are reminders that Earth itself is alive and capable of mysteries we have yet to master. Why plate tectonics began on Earth is still debated. The surface of our planet is alive with motion. Continents drift, mountains rise, and oceans open and close, all driven by the movement of tectonic plates. Without plate tectonics, Earth would not have its landscapes, its earthquakes, or its volcanoes. Life itself may depend on this restless churning. But why did it begin here and not on other planets? Mars and Venus have no active tectonics. Their crusts are stagnant, locked in place. Somehow, billions of years ago, Earth's crust fractured into giant plates that slide and grind endlessly. Did water act as a lubricant, weakening rock and allowing movement? Did internal heat reach just the right balance between strength and flow? Or was it triggered by ancient impacts that cracked Earth's crust? We don't know. Computer models offer competing answers, but none explain why Earth alone developed this feature. Without plate tectonics, the carbon cycle that regulates climate might fail, leaving the planet barren. Plate tectonics is what makes Earth dynamic and habitable. Yet the reason it began, and why it is unique in the solar system, is still an unsolved puzzle. The origin of Earth's water is still uncertain. Water covers most of Earth, filling oceans, rivers, and clouds. It is essential to life. And yet, its origin remains one of science's great mysteries. Did water arrive on asteroids and comets, delivered during the chaos of the early solar system? Some evidence supports this, as many space rocks contain ice. But the chemical fingerprints of Earth's water don't always match those of comets. Another idea is that water was present from the beginning, trapped deep within Earth's mantle, slowly rising to the surface over eons. Perhaps both are true, some water born here, some brought from space. But the balance is still debated. What we do know is that Earth is unusual. Neighboring planets like Venus and Mars are dry, their water lost or locked away. Something about Earth allowed oceans to gather and remain stable. Water is so ordinary that we forget its strangeness. Every drop you drink carries the mystery of its origin, a riddle stretching back to the birth of our world. The far side of the moon looks strangely different, and we don't know why. For millennia, humans saw only one face of the moon. The far side remained hidden until spacecraft revealed it in the 20th century, and what we saw was surprising. The near side, the face we know, is covered with dark maria, vast plains of cooled lava. The far side looks nothing like it, rugged, mountainous, with almost no maria at all. Why should the two faces of the same moon be so different? One idea suggests that the moon once had uneven heating, with Earth's gravity baking one side more intensely. Another proposes that an ancient collision reshaped one hemisphere but not the other. Some theories involve internal dynamics, differences in crust thickness or volcanic activity. But no explanation fits perfectly. The moon should be symmetrical, yet it isn't. Its hidden face carries scars and secrets that defy simple answers. Even now, as spacecraft orbit and landers touch its surface, the far side of the moon keeps its mystery, as though it is still half a stranger to us. Earth's core powers a magnetic field, but the details remain unclear. Deep beneath our feet, more than 3,000 kilometers down, lies Earth's core, a ball of molten iron and nickel, surrounding a solid inner sphere. Its motion generates Earth's magnetic field, shielding us from solar winds and cosmic radiation. Without it, our atmosphere might be stripped away, leaving Earth barren like Mars. But despite its importance, we don't fully understand how it works. We cannot drill to the core, so we rely on indirect clues: seismic waves, magnetic records, computer models. We know the outer core flows like a liquid, and that this motion powers the geodynamo. But why Earth's field sometimes weakens, wobbles, or reverses entirely is still uncertain. Other planets puzzle us further. Mars once had a magnetic field but lost it. Why did Earth keep its protective shield while Mars did not? The beating heart of our planet remains hidden from direct study. We feel its effects every day, in compasses, in auroras, in our very survival. But its inner workings remain mysterious. Earth's magnetic poles sometimes flip, and the cause is still unknown. Every so often in Earth's history, the magnetic poles switch places. North becomes south, south becomes north. These reversals are recorded in ancient rocks, showing a flip-flop pattern stretching back millions of years. The last full reversal happened about 780,000 years ago. But why do they happen? Scientists believe turbulence in the liquid outer core, the engine of Earth's magnetic field, sometimes becomes unstable, causing the field to collapse and rebuild in the opposite direction. But the exact trigger is unclear. Sometimes the flips are quick, sometimes they take thousands of years, and sometimes the field only weakens without fully reversing. The mystery deepens when we consider the effects. During a reversal, the field weakens, exposing Earth to more radiation from space. Would that disrupt ecosystems? Did past reversals influence evolution? We don't know. All we know is that Earth's magnetic field is not permanent. One day, north will again become south, and the reason why remains hidden in the depths. Ice ages come and go, and we still don't know what drives them. For millions of years, Earth's climate has swung between ice ages and warmer periods. Vast glaciers have advanced and retreated, carving landscapes and reshaping continents. But why this cycle happens is still debated. Some explanations point to changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter how sunlight reaches the planet. Others suggest volcanic eruptions, shifting ocean currents, or carbon dioxide feedback loops. Perhaps all of these combine in ways we don't yet fully understand. What is certain is that the rhythm of ice and thaw has shaped human history. Our ancestors migrated, adapted, and survived in the shadows of glaciers. Civilizations rose as climates warmed. But the underlying cause, the engine of these repeating freezes, remains unclear. The ice ages remind us that Earth's climate is never fixed, but part of a mystery far larger than ourselves. Mass extinction strikes suddenly, and their causes remain unsettled. 5 times in Earth's history, life has nearly been wiped out. The dinosaurs' extinction 66 million years ago is the most famous, but even greater catastrophes came before, like the Great Dying 250 million years ago, when most life on Earth vanished. Asteroid impacts, supervolcanoes, climate shifts, and changing oceans have all been proposed as causes. Sometimes the evidence points clearly, as with the asteroid that struck at the end of the Cretaceous. Other times it is murky, multiple disasters overlapping, creating cascades of collapse. Why some species vanish while others survive is equally mysterious. Why did mammals endure the asteroid strike while dinosaurs perished? Why do some extinctions unfold in slow decline while others happen in a geological instant? Mass extinctions are reminders of life's fragility, but also of its resilience. Each one cleared the stage for new forms of life to rise. But the forces behind them, sudden, devastating, and unpredictable, remain only partly understood. Saturn's rings appear young, and we don't know how they formed. Saturn's rings are among the most breathtaking sights in the solar system, vast bands of shimmering ice and dust encircling a giant planet. They stretch for hundreds of thousands of kilometers, yet they are astonishingly thin. sometimes only a few dozen meters deep. For centuries, we assumed they were as old as Saturn itself, more than 4 billion years. But recent evidence suggests otherwise. The rings appear strangely clean, made mostly of bright ice with little dust. If they were ancient, they should be darker, dirtied by micrometeorite impacts over eons. Measurements from NASA Cassini spacecraft hinted that the rings may be only a few 100 million years old, a blink of an eye in cosmic time. If true, how did they form so recently? Perhaps a moon wandered too close and was torn apart by Saturn's gravity. Perhaps comets or asteroids shattered, leaving debris that spread into rings. But no explanation is certain. Saturn's rings may be temporary, destined to fall into the planet over the next 100 million years. We are living in the brief era when Saturn wears this dazzling crown. The mystery of their origin remains one of the solar system's most beautiful unsolved puzzles. Uranus spins on its side, and no one knows why. Among the planets, Uranus is an oddball. Instead of spinning upright like Earth, it rolls through space on its side. Its axis is tilted by 98 degrees, leaving it rotating almost horizontally. For part of its orbit, one pole points directly at the sun, bathing that hemisphere in decades of sunlight, while the other lies in darkness. How did Uranus end up this way? The leading idea is that, long ago, a colossal impact with a protoplanet knocked it onto its side. But such a collision should have left behind signs, like a large moon or a scar in its atmosphere. Another theory suggests multiple smaller impacts slowly tilted the planet. Still others propose that gravitational interactions with giant planets in the early solar system pulled Uranus into its strange posture. Whatever the cause, Uranus remains unique. Its sideways spin creates bizarre seasons and may even influence its magnetic field, which is also oddly tilted and offset. No probe has visited Uranus since Voyager 2 in the 1980s, leaving most of its mysteries unsolved. Until we return, Uranus rolls quietly on its side, carrying a cosmic riddle that no other planet shares. Venus rotates backwards, and its strange past is still debated. Venus, often called Earth's twin, is nearly the same size and mass as our planet. But it is also profoundly strange. One of its oddest features is its rotation. While most planets spin in the same direction they orbit the Sun, Venus rotates the other way. On Venus, the sun rises in the west and sets in the east. Even stranger, a single day on Venus lasts longer than its year. How did this happen? One idea is that Venus was struck by a massive object early in its history, flipping its spin. Another suggests tidal interactions with the sun slowly reversed its rotation. Still another theory imagines Venus once spun rapidly like Earth, but its thick atmosphere and internal dynamics gradually slowed and reversed it. No theory fully explains the planet we see today. Its atmosphere, dense with carbon dioxide and sulfuric acid, may hold clues, but for now, Venus keeps her secrets. Beneath her perpetual clouds, Venus turns slowly, backwards, and against expectation, a reminder that even familiar-looking worlds can hide the strangest histories. Neptune is full of storms we don't fully understand. At the edge of a solar system, Neptune howls with winds faster than any on Earth, reaching nearly 2,000 kilometers per hour. Vast storms swirl across its deep blue atmosphere, appearing and vanishing in ways that baffle scientists. The most famous, the Great Dark Spot, was discovered by Voyager 2 in 1989. It was a storm the size of Earth, but when the Hubble Space Telescope looked a few years later, it had disappeared completely. Other dark spots have since appeared, shifting across the planet sometimes breaking apart or fading without warning. Why does Neptune, so far from the Sun, have such violent weather? Its distance means it receives little solar energy. Some believe Neptune's internal heat drives the storms, while others think dynamics in its atmosphere amplify small changes into massive tempests. But the details remain unclear. Neptune remains a distant, storm-racked world, visited by only one spacecraft. Its mysterious weather shows us that even in the frozen reaches of the solar system, chaos can reign. Jupiter's great red spot has raged for centuries, and its future is uncertain. For as long as humans have pointed telescopes at Jupiter, the great red spot has swirled in its atmosphere, a storm so large it could swallow Earth whole. It has been raging for at least 350 years, perhaps much longer. But why it began, and why it has lasted so long, remain mysteries. The storm is an anticyclone, spinning counterclockwise in Jupiter's southern hemisphere. Powered by the planet's immense atmosphere, it seems almost eternal. Yet in recent decades, scientists have noticed that it is shrinking. Once wide enough to fit 3 Earths across, it now spans barely more than 1. Some predict it may fade away entirely in the coming century. Why did the storm form where it did? Why has it lasted centuries when storms on Earth last only days or weeks? And will it truly vanish, or revive itself in cycles we don't yet understand? The Great Red Spot is a cosmic paradox, at once ancient and fragile. It remains one of the most iconic mysteries in the skies. Comets cluster in a distant cloud we've never seen directly. Comets, with their glowing tails, have fascinated humans for millennia. They swoop in from the edges of the solar system, loop around the Sun, and then vanish again into the dark. Astronomers believe these icy wanderers come from a vast reservoir far beyond Pluto, the Oort cloud. The Oort cloud is thought to contain trillions of icy bodies, leftovers from the birth of the solar system. It stretches so far that its edge may blend into interstellar space. And yet, despite being the source of comets, it has never been observed directly. The objects are too small, too distant, and too faint. We know the Oort cloud only from the comets it sends us, visitors that hint at the vast unseen population beyond. Was it formed by the scattering of early planets? Does it extend farther than we imagine? We don't know. The Oort cloud is the great unseen frontier of our solar system, a ghostly shell surrounding us, full of secrets we have yet to glimpse. Many moons hide oceans beneath their ice, but we don't know what lives there. Beyond Earth, water is not rare. Moons like Europa, Enceladus, and Titan all hide oceans beneath shells of ice. Some of these oceans may be larger than all the seas on Earth combined. They are kept liquid by the gravitational pull of their planets, which needs the moon's interiors and generates heat. What makes these oceans exciting is their potential for life. On Earth, where water exists, life almost always follows. Hydrothermal vents deep in our seas thrive with creatures independent of sunlight. Could similar ecosystems exist beneath alien ice? We have hints. Enceladus sprays plumes of water into space, rich with organic molecules. Europa's cracked surface shows signs of activity below. But we cannot yet see into these oceans directly. What strange forms of life might swim there? Simple microbes, or something far more complex? Until we explore these hidden seas, the answer remains locked beneath ice, waiting in the dark. Enceladus sprays water into space, and we don't know what stirs below. Saturn's small moon Enceladus looks unassuming, just a bright, icy sphere. But when NASA Cassini spacecraft flew past, it discovered geysers erupting from cracks near the South Pole, spraying water vapor and ice grains far into space. These plumes contained salts, organics, and even signs of chemical reactions that, on Earth, would hint at habitability. Beneath the surface, Enceladus hides a global ocean, kept warm by Saturn's tidal pull. The geysers may be vents connecting this ocean to the surface. But what drives the eruptions? Are they powered by hydrothermal vents at the seafloor, like those on Earth's oceans that teem with life? Or are they fueled by some other unknown process? Enceladus is small, barely 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Its plumes offer a direct sample of its hidden sea. But until we return with new missions, the mystery of what stirs beneath its ice remains unsolved. Titan has seas of methane, and something keeps replenishing them. Titan, Saturn's largest moon, is a world both familiar and alien. It has lakes and seas, rivers and rain, but instead of water, they are made of liquid methane and ethane. Titan's skies are hazy, its surface sculpted by weather that is utterly unlike Earth's. Here's the mystery. Methane in Titan's atmosphere should be destroyed by sunlight over time. If that were the case, the methane seas would have long since vanished. Yet they are still there. Something, deep underground or hidden within Titan's chemistry, keeps replenishing them. Some suggest cryovolcanoes may release methane from Titan's interior. Others imagine chemical processes we don't yet understand. Intriguingly, some researchers note that methane is also a potential biosignature, a sign of life. Could Titan's methane be biological in origin? We don't know. Titan's methane cycle mirrors Earth's water cycle in eerie ways. But the source that sustains it, the hidden pump that keeps its seas full, remains a mystery, waiting to be solved. Mars once had flowing rivers, but we don't know where the water went. Billions of years ago, Mars was a very different world. Vast river valleys carved the surface. Deltas and lake beds mark where water once pooled. The planet may even have had oceans. Today, it is dry and frozen, with only thin wisps of water vapor in the air. What happened to all that water? Some may be locked as ice beneath the surface. Some may be trapped in minerals. Much of it may have escaped into space when Mars lost its protective magnetic field. But the full story is unclear. Mars is littered with evidence of its watery past, yet its present is a desert. Did the water disappear slowly or in sudden shifts? Could liquid water still flow underground today, hidden from our view? The fate of Mars's rivers remains one of the greatest planetary mysteries. To solve it may be to understand whether the planet once supported life, and whether it still could. Mathematics describes the universe with uncanny accuracy, but we don't know why. Mathematics is a language of patterns, a human invention built from numbers, symbols, and logic. Yet astonishingly, it describes the universe with almost perfect precision. Equations dreamed up on paper turn out to govern stars, atoms, and galaxies. Einstein's equations predicted black holes before anyone had seen one. Maxwell's formulas described radio waves long before they were detected. Why should abstract symbols map so exactly onto reality? Some scientists argue that math is discovered, not invented, that it reveals truths built into the structure of the cosmos. Others suggest math is a tool shaped by human minds, tuned by evolution to fit the patterns we see. But neither answer explains the eerie accuracy of mathematics in physics. Why should the same formulas describe both the arc of a thrown ball and the motion of distant planets? Mathematics is at once a human creation and a universal key. Why it works so uncannily well remains one of the deepest mysteries of existence. The constants of nature seem fixed, yet their values remain unexplained. Every law of physics rests on constants: the speed of light, the charge of an electron, the strength of gravity. These numbers define how the universe works. Change them slightly, and stars might never form, chemistry might not exist, life might be impossible. But why do they have the values they do? Scientists measure these constants with exquisite precision, but no theory explains why they are what they are. Some suggest they are simply accidents of the universe. Others imagine a multiverse where countless universes exist, each with different values, and we just happen to live in one where life is possible. But these remain speculations. The constants of nature are like settings on a cosmic dial, fixed, precise, and unexplained. They are the background music of the universe, a melody we can hear but not compose. We don't know if true randomness actually exists. Flip a coin, roll dice, shuffle cards. Randomness seems obvious. Yet physics makes the question stranger. At the quantum level, particles behave unpredictably. An electron may appear here or there. A radioactive atom may decay now or later, with no cause we can see. Is this true randomness, or just complexity beyond our understanding? Einstein famously resisted the idea, saying, "God does not play dice with the universe." He believed hidden laws must govern quantum events. But decades of experiments suggest otherwise. Quantum mechanics really may be irreducibly random. Still, some scientists believe deeper rules are waiting to be discovered. Others think randomness is woven into the very fabric of reality. If true randomness exists, then uncertainty is not just ignorance. It is part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at the heart of physics. Time itself is still one of science's greatest mysteries. We live in time. We feel it flow, second by second, carrying us from past to future. Yet science cannot fully explain what time is. Einstein showed that time is not absolute. It bends and stretches depending on speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way arrow? Why does the past feel fixed, while the future remains open? Some physicists think the arrow of time is tied to entropy, the tendency of disorder to increase. But this only pushes the question back. Why was the universe born in such an ordered state? Others suggest time itself might be an illusion, a trick of human perception. Time governs every heartbeat, every thought, every life. Yet its true nature remains one of the most profound mysteries we face. Matter exists, but antimatter nearly vanished. We don't know why. When the universe began, the Big Bang should have created equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have disappeared in a flash, leaving no stars, no planets, no people. And yet, here we are. Somehow, matter won. Why did matter gain the upper hand? Experiments show that matter and antimatter behave almost identically, but with tiny asymmetries. These slight differences may have tilted the balance in the early universe, but they do not seem large enough to explain why anything exists at all. Somewhere in the physics of the early cosmos lies the reason why there is something instead of nothing. Until we find it, the victory of matter over antimatter remains an unsolved riddle. Particles have mass, but we still don't know what gives it to them. Everything around us has mass, from stars to sand to our own bodies. But what gives particles mass at all? For decades, this was one of physics' biggest mysteries. The discovery of the Higgs boson in 2012 confirmed that an invisible field pervades the universe. As particles move through it, they acquire mass, like swimmers pushing against water. Without this field, matter as we know it could not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field itself exist? Why does it have the strength it does? And why do different particles interact with it so differently? The Higgs discovery opened the door, but behind it lies a deeper mystery still. Mass feels solid and obvious, but its origins remain partly hidden in the invisible fields of the cosmos. Reality may be continuous, or it may be pixelated. No one knows. To our eyes, reality feels smooth. Space seems infinitely divisible, like a line you can cut forever. But at the smallest scales, physics may be different. Some theories suggest the universe is pixelated, made of tiny, indivisible units, like the pixels on a screen. This smallest length, the Planck scale, is far beyond what we can observe, but it might be the foundation of everything. If reality is pixelated, then space and time themselves are not smooth, but granular. The rules of physics would need rewriting, but so far, no experiment has confirmed this. Whether the universe is continuous or digital remains one of the strangest questions in science. The answer could reveal the true texture of reality itself. There may be a smallest possible length of space, but we haven't found it. Physics pushes us to ever smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turned out to be made of quarks. Yet at some point, there may be a smallest length, a limit beyond which smaller has no meaning. This is thought to be the Planck length, unimaginably tiny, about 100 billion times smaller than a proton. At this scale, space may no longer be smooth, but foamy and uncertain, a quantum haze. But no experiment can reach it yet. If space has a smallest unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest brick of existence. Whether such a limit exists remains one of the deepest mysteries of physics. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on laws, gravity, electromagnetism, quantum mechanics. They are elegant, precise, and consistent. But they could have been otherwise. Why this set of laws and not another? Why a universe where stars can form instead of one where matter collapses or drifts apart? Some scientists imagine countless universes, each with different laws, and ours is simply one where the conditions allow life. Others think deeper principles, still unknown, fix the laws in place. But for now, the origin of the laws themselves remains unexplained. We can describe the rules. We cannot yet explain why these rules, and not others, are written into reality. And perhaps the greatest mystery of all, whether we will ever truly understand any of this. Science has carried us far. We have mapped galaxies, split atoms, decoded DNA, and walked on the moon. Each answer reveals more questions. Each discovery opens new mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, the nature of time itself. Or perhaps there will always be questions just beyond our reach, mysteries that cannot be solved because they are woven into the fabric of existence. The greatest mystery may not be the universe itself, but our place within it, whether human minds can ever truly comprehend the totality of reality. As you drift to sleep, you might hold that thought gently. that curiosity itself is part of the mystery. To wonder is to be human, and to seek is to be alive. The questions may never end, but neither will our search. You've just traveled through 100 of science's greatest mysteries, questions that stretch from the cells in our bodies to the edges of the universe itself. Each one is a reminder that for all we've discovered, the world remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we've touched tonight: the hidden spark of consciousness, the riddles of aging and memory, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and the fabric of reality itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations. And still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery, an invitation. The fact that we don't yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they pull you toward rest. Like the slow rhythm of waves on a shore, the questions themselves are soothing. They don't need answers tonight. They only need to be carried, like starlight across a dark sky. So let your breathing fall into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we've explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you. And you, at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. If you happen to still be awake, you can go ahead and watch the next video when you're ready. But for now, there's nothing left to do. No answers to chase. No puzzles to solve. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep. Good night, and may your dreams be filled with wonder.